section 3.3, multiplying vectors. No longer just adding or subtracting. This is next level stuff. So turns out we have 3 different methods of multiplying vectors. The first one is multiplying a vector like vector z by a scalar c. And the result here is we will get a new vector out. The magnitude of the new vector is just going to be the magnitude of vector z times c. Cool. It's going to be the same direction as vector z as well, because c doesn't change the direction, except it could potentially flip it if c is negative, but that's about all that c can do. It's going to have to keep it pointed either that way or the exactly opposite way. So to achieve this, we can simply multiply each of the components of vector z by c, each of those scalar components, which helps us out, right? So if we have z is equal to negative 3i hat plus 5j hat, sorry, I don't have the hats there, the bold is to represent that. Then if we want to multiply it by 5, each of those components gets 5 times bigger. The direction hasn't changed, it's just scaled up. So 5 times z vector becomes negative 15i hat plus 25j hat. Awesome. If we want to divide a vector by a scalar, we can just multiply by 1 over that scalar. So that is our first method of multiplying vectors. Our second method is multiplying 2 vectors, and this is known as the scalar product, or it's also called the dot product. It's called the scalar product because it results in a scalar. It gives you a non-vector as a result, which is pretty interesting and fairly unique. A and B are magnitudes, and phi or phi is the angle between the directions of the 2 vectors. So here's a way that we can calculate the dot product. This is a really handy equation. The way the dot product is written, or the scalar product, is vector A is dotted with vector B. So here the way you draw your multiplication sign matters. If you draw it with a big dot, then that's a sign that's the dot product. And again, it can be calculated with these 2 magnitudes times cosine of the angle between them. So if I draw this out, we could have vector A, and then we could have vector B, and then the angle between them, whichever way they're pointing, is given by the phi or the phi. And the reason we use phi or phi, whichever you prefer, is that this isn't necessarily defined relative to the x-axis. It's just the angle between them, no matter which way these are pointing. So they could be pointing horizontally, or they could be pointing at crazy angles. All that we care about is what angle they are between each other. With the dot product, the commutative law applies, so we can do the dot product in component form. And if you do this in component form, what you'd find when you dot this all out is that when you have I hat dotted with I hat, that would have an angle of 0 there. Cosine of 0 is equal to 1. And so those pieces would last. And so you keep the AX and the BX. And so that's why we get this AX times BX here. That said, if you take the AX I hat and you dot it with the J hat, now those are at a right angle. So the angle between them is 90. Cosine of 90 is 0. So those pieces would disappear. That said, what if we have y times y, right? So ayj hat times byj hat. Well, now these are both in the same direction again, angle of 0, so it totally lasts. And so that's how we ultimately arrive at this definition, alternative definition, and a great way to calculate the dot product. That it's just going to be the like components multiplied by each other and then adding each of those together. With the dot product, we will often use both of these definitions interchangeably. Sometimes you'll use the one to calculate the dot product, and then you can thus calculate the angle between any 2 vectors, which is a really powerful technique. So a little more about the dot product. A way to think about it is it's the product of the magnitude of one vector times the scalar component of the other vector in the direction of the first vector. In other words, we're trying to find out how much our 2 vectors point in the same direction. So if we take the scalar component of one vector to see how much it's pointing along the same, and then multiply those together. So that's what's shown here in the picture. We have vectors A and B, and we can take the component of A that is along B, right? And we'd get that there's some amount of A along B. Well, how would we calculate that amount of A along B? That would come from A times cosine of the angle between them. So we could take A cosine phi times B, and that's what's shown here. Similarly, we could look at the shadow of how much of B is pointing along A. That's what they tried to do here. And this piece is given by B cosine phi. That's how much of vector B points along vector A. So you can use either projection of one vector onto the other to be used. We're just trying to see overall how much they are pointing in the same direction. So to multiply a vector by the projection, multiply the magnitudes, right? Where since there's no vector symbol above this A or this B, it's just the magnitude of said vector. Note here, if the angle between the two vectors is 0 degrees, then the component of one vector along the other is a maximum. And so also is the dot product. You get the largest amount if they're pointed in exactly the same direction. If instead the angle is 90 degrees, the component of one vector along the other is 0. They're pointing in completely different directions. So the dot product is 0 as well. Right. So let's look at an example. I'll clear my drawings here. Vectors C and D have magnitudes of 3 and 4 units respectively. What is the angle between directions of vector C and D if C dot D equals 0, 12 units, and negative 12 units? So I'd like you to think this through, then you can go ahead and move forward with the video after you've come up with an answer. So go ahead and pause. Did you pause? Right. Well, let's see. For them to be 0, we know that the dot product relies on this cosine of the angle between them. So when is cosine equal to 0? Well, it's going to be equal to 0 when it is at 90 degrees, right? So that tells us about that one. What about when it's at 12 units? For it to be 12 units, that tells us they need to be pointed in the same direction, right? That's where we have the maximum result of the dot product, and we use the full magnitude of 3 times 4 to get 12. Cosine of 0 degrees is 1. Then finally, negative 12. How would we get a negative sign? Well, when is cosine negative? Cosine's negative if it is 180 degrees, or if the vectors are pointed exactly opposite each other. In that case, we would get a negative times the 3 times the 4 to get negative 12. So that one would be 180. All right. Third, last but not least, our third method of multiplying vectors is again multiplying two vectors, but this one's known as the vector product. It's also called the cross product very commonly. And the cross product does produce a vector, which is why it's called a vector product, right? So that's fairly logical. The magnitude of said vector is given by this equation, A times B times sine of the angle between them. So it's very similar to the dot product equation, but this one's only the magnitude of the resultant vector, and it uses a sine instead of a cosine. The direction is perpendicular to both the original vectors. So the cross product will give us a perpendicular resultant. Very cool. The direction is determined by the right-hand rule, which we'll cover in just a moment. What we're going to do for the right-hand rule is we'll place the vectors tail to tail and then sweep the fingers from the first to the second, and the thumb will point in the direction of the resultant. So we'll see this in just a moment. If A and B are parallel or anti-parallel, they're going in the same direction or the opposite direction, then the cross product is 0. The magnitude is at a maximum when vectors A and B are perpendicular to each other. Right, now what about this right-hand rule? Well, I really appreciate this depiction of it. I'll clear my drawings again. That we start with our fingers pointed towards one vector, and we sweep them or bend them towards the other. In order to do that, our thumb would then give us the direction of the resultant. So they start with them pointing towards A, bend them towards B, and then the thumb is pointing perpendicular to the tabletop. Similarly, if we instead have B times crossed with A, we would start with B and then bend towards A, and our thumbs would point down. Now this highlights an important idea, and that's that the cross product is not commutative. B cross A is the negative of A cross B, right? A cross B gave us a thumbs up, B cross A gave us a thumbs down, the exact opposite direction. Now to evaluate the cross product, we'd have to distribute over all the components. And what we'd see is all the like components, I hat crossed with I hat, would give us 0 because we'd have sign of 0, which is 0. But all the unlike components, I hat crossed with j hat, would give us a perpendicular vector that is non-zero. So I hat and j hat produce a k hat. So by expanding this out, following it through all the components, we arrive at this equation, which is not very simple or very elegant, but it does work. So you can follow this equation to calculate the cross product. I'll show you one other possible technique in the next video, but if you just want to use this equation and plug and chug to your heart's content, it will work out.